Welcome back to a course on calculus RS integration. In this lecture, we are going to talk about few more theorems on RS integration. The first theorem that we are going to see is if UPF alpha minus LPF alpha is less than epsilon, and this is holding for some partition P. So whenever they say it is holding for some partition P, we must have the basic assumption that f is some function on the interval closed in. Okay, this is P is a partition of some closed interval a comma b. This has to come to our mind. Okay, and this is holding for some partition P and some positive quantity epsilon. Then we have to prove for every refinement of this P. For every refinement of P, we have UP star F alpha minus LP star F alpha is less than epsilon for the same epsilon. This is what we have to prove. This idea we have proved using the using some diagrammatic ideas that we used in the previous theorem itself. Now we are going to prove it formally. Now let us see how to prove this. Okay. Initially, let us assume that UPF alpha minus LPF alpha is less than epsilon, and we take some refinement of P. Then what do we get by the theorem that we have already seen, that is LPF alpha is less than or equals LP star F alpha, and UP star F alpha is less than or equals UPF alpha. And from the first thing, that is using the lower sums, what we shall write is that invert the we just invert to get the negative value of this. Once you get this relation, you just mark it as 2. Now going back here and see, this is our equation 1. Now we are just going to do 1 minus 2. So when we do 1 minus 2, what are we going to get? We will get UP star F alpha minus LP star F alpha is less than or equals UP F alpha minus LP F alpha, and we know this quantity is less than epsilon, and hence what we get is UP star F alpha, and hence we get the requirement. Okay, we are done. Now we'll check the second part of this theorem. Here it is given that UP F alpha minus LP F alpha is less than epsilon holds for some partition P, and we take Si and Di be the arbitrary points of this subinterval xi minus 1 comma xi. Okay, in the sense, if this is my x0, if this is my xn, in between we choose some subinterval. In this subinterval we have taken 2 points. Okay, some arbitrary points. It is given. It is not specified that only this interval you will have to take, only this interval you will have to take. They have not specified anything. It may be any subinterval based on this partition, and in that subinterval we are choosing 2 arbitrary points. Then we will have to prove summation I runs from 1 to n absolute of f of si minus f of ti delta alpha I. Hope you know what is delta alpha I. Your delta alpha, okay, let me write here. Your delta alpha I is alpha times of xi minus alpha, sorry, it is not alpha times of xi, it is alpha of xi minus alpha of xi minus 1. Remember, this alpha is a monotonically increasing function, right? Okay, let us proceed to prove this with the same assumptions. With the same assumptions as in second part of this theorem, we are assuming one more thing, that is the function f is RS integrable. Then we are going to have the third one. Let us continue to prove the second and third part of this theorem. Okay, in the second part of this theorem, we are given with some partition, and the partition is this one. Okay, in this, in the subinterval xi minus 1 comma xi, we find the supremum and infimum values. Okay, if we find the supremum and infimum values for any two things inside the subinterval, we'll get the image of these 2 points si and ti under f to be in the interval mi comma big Mi, because small mi is the infimum value, big Mi is the supremum value. Then this is what is going to happen, right? So this value is bounded between Mi and big Mi, and the same goes for f of si too. Now If you revert this inequality with the negative sign, what are you going to get? Minus mi less than or equals minus ti less than or equals minus mi. Let us mark them as equations 4 and 4, and now using 4 and 5, what do we get is that simply we just add 4 and 5. So mi minus mi less than or equals f of si minus f of ti, which is less than or equals big mi minus small mi. Right? Now, the small mi minus big mi is written as minus times of mi minus small mi. So from this, what we can do is that absolute of f of si minus f of ti is smaller than or equals mi minus small mi. So when if you multiply delta alpha I along with it and take the summation, this is what you are going to get. And now you can split these quantities. When you split these quantities, this is your UPF and this is your LPF. Okay, and finally this quantity is less than or equals UPF alpha minus LPF alpha. Actually here you have equal sign because this is exactly equal to UPF alpha and this is exactly equal to LPF alpha. We just do the things and now just not equating, comparing the first this quantity and this quantity, we have less than or equal sign in between. Hence we get summation I runs from 1 to n absolute of f of si minus f of ti multiplied with delta alpha I is less than or equals UPF alpha minus LPF alpha, which is less than epsilon. Right? We are done with the second part of this theorem. Now, in the third part, we are given that f is Riemann-Stieltjes integrable. Along with the hypothesis that we have taken in part 2 of this theorem, we have one more thing, that is f is Riemann-Stieltjes integrable. If f is Riemann-Stieltjes integrable, lower RS integral is same as that of the upper RS integral, and that is what we mean by the RS integral that we have written, and we take that as equation 6. Also, from the hypothesis of part 2 of this theorem, we take UPF alpha minus LPF alpha is less than epsilon, and we take if we take any 2 points in the subinterval xi minus 1 comma xi, then of course the image of these 2 points under f is going to be in the interval of the infimum and the supremum of the function in the subinterval. Okay, and this tells us that again the same ideologies we are doing. Now we take the summation and actually we multiply delta alpha I and take summation. This is what we are going to get. Okay, and by the definition of lower and upper sums, this f of ti, what is this f of ti? This f of ti is uh, somewhere between mi and mi, right? So by definition, this is your LPF alpha and this is your UPF alpha and this is your LPF alpha, and we get this thing. Now the assumption that we have is UPF alpha minus LPF alpha is less than epsilon. From this we shall write UPF alpha is less than epsilon plus LPF alpha. And here we are not actually taking supremum. We know that any quantity, okay, supposing, let me take another function, g of x is defined on x in a, and this g of x will be less than or equals supremum of g of x over a, right? So this is going to be there for any function. Okay, that is what we have done here. So this quantity, this LPF alpha is smaller than or equal supremum of LPF alpha. So we have just made use of this thing. Actually, we'll have a equality here too. So by definition, this is our lower Riemann integral. Here we have the equality, and comparing this UPF alpha with this thing, what we get is our equation 8. Okay, we again start with the same thing. We bring this epsilon to this side and take LPF alpha to the other side. We get this one. So from which here I have given you in a separate way, but here this infimum of UPF alpha, this quantity will be lesser than or equals any quantity. If it is going to be for the supremum case, for the infimum case, what is going to be the case? Less than or equals g of x. Right? So this is going to happen. That is what we have written. And by definition, infimum of UPF alpha is the upper RS integral. So we come this. Here, since the function is assumed to be a Riemann integrable, the lower Riemann integral as well as the upper Riemann integral becomes the Riemann-Stieltjes integral, actually RS integral. Okay. So now using inequality 7, 8 and 9, what we get is integral fd alpha minus epsilon is less than LP f alpha less than summation I runs from 1 to n f of ti delta alpha I less than UP f alpha minus less than epsilon plus integral a to b fd alpha. Here we are not in order to prove this theorem, we are not interested in this LPF alpha or UPF alpha. We'll just have to compare this integration, this summation and this integral parts. So using these three alone, we write the inequality, and here we are subtracting actually there is a step missing. Let me do it here. So if we subtract integral a to b fd alpha from these things, what we are going to get is minus epsilon less than summation I runs from 1 to n f of ti delta alpha I minus integral a to b fd alpha less than epsilon. And this is absolute of summation minus integral is less than epsilon, and this completes the proof.